All right, welcome back, everyone, for another deep dive. You know, we like to really dig into a topic, and today's no different. If you're an engineering student, I bet you've run into this. You open a textbook on material science, and it's like suddenly you need a PhD just to understand the intro paragraph.
Oh yeah, it can definitely be a bit overwhelming sometimes, especially when you're first getting into it. So much terminology, all these different concepts, and it can be hard to see the forest for the trees.
Exactly. But don't worry, we're going to make it super clear. Our mission today is to break it all down into plain English and focus on the core principles of engineering materials technology. Like the really essential stuff that you actually need to grasp to, actually work with these materials in the real world as an engineer.
I like it cutting through the clutter and getting straight to the fundamentals.
Yeah. So we'll be using a great source today, Engineering Materials Technology by W. Bolton. This book's a classic, but it's pretty dense. So we're going to extract the nuggets of gold, the essential concepts. And we'll be doing it using everyday language, so even if you're just starting out, you'll be able to follow along.
That sounds like a good plan.
Let's start with the absolute basics, the atom. We all learned about atoms in high school, but we need a solid refresher because, it's the foundation of everything in material science. It's like trying to build a house without understanding bricks.
Couldn't agree more. Atoms are the building blocks of everything. They're the smallest unit of an element that retains the chemical properties of that element.
Okay, so let's break it down. Each element is defined by a specific number of protons in its nucleus, right? That's the atomic number, like hydrogen has one, helium has two, and so on.
Exactly right. The atomic number is like the element's fingerprint. It's a unique identifier. And because atoms are electrically neutral overall, they have to have an equal number of electrons orbiting around that nucleus to balance out the positive charge from the protons.
Now, those electrons aren't just randomly buzzing around the nucleus, right? There's some kind of order to it.
That's a great question, and the answer is yes. There's definitely order in the way these electrons are arranged, and that order actually dictates a lot about how the atom interacts with other atoms. One way to visualize this order is with the Bohr model. You can think of it as the atom's solar system, with the nucleus as the sun and the electrons as planets orbiting around it.
So these electrons occupy specific orbits, or shells, at different distances from the nucleus. The book mentions K, L, M shells, and so on, kind of like those planetary orbits. And each shell can hold only a certain number of electrons before a new shell has to start.
That's right. It's all about the energy levels of those electrons. The shells closer to the nucleus have lower energy levels and can hold fewer electrons. For example, the K shell, the innermost one, can only accommodate 2 electrons, while the next one out, the L shell, can hold up to 8.
Okay, I'm starting to see the pattern here. Can you give me a few concrete examples, with real atoms to help solidify this picture?
Sure. Let's take hydrogen, the simplest atom. It has just one proton and one electron, right? So that single electron occupies the K shell. Now, helium has 2 protons and 2 electrons, both of which fit nicely in the K shell, filling it up.
So helium's super stable because its outer shell, in this case the K shell, is full.
Exactly. That full outer shell is what gives the noble gases their stability, their reluctance to react with other elements. Now, move on to lithium. It has 3 electrons, 2 fill up the K shell, and the third one starts a new orbit in the L shell.
So the L shell starts filling up when the K shell's already got its maximum number of electrons.
Precisely. And you can see this pattern continue. Carbon, for instance, has 6 electrons, 2 in the K shell and 4 in the L shell. If you need a visual aid, Table 1.1 in the book shows all these electron configurations really clearly.
Okay, I'm getting a much better grasp of how those electrons hang out around the nucleus. Now, how does all of this electron arrangement, connect to how atoms bond with each other to form different materials?
That's where the real magic happens. The way those electrons are arranged, particularly in the outermost shell, called the valence shell, determines an atom's bonding behavior. Atoms, they're not really loners. They're social butterflies in the atomic world. They like to interact with other atoms and form bonds to become more stable.
So it's like they're trying to achieve a full outer shell, just like helium with its full K shell.
Exactly. You got it. Atoms are happiest or most stable when they have a full outer shell. It's like completing a puzzle. And to achieve this full shell, they'll engage in different types of bonding.
And one of the most common types of bonding is ionic bonding. That's where one atom actually donates an electron to another, right?
To spot on. The classic example of ionic bonding is sodium chloride, which is just good old table salt. Let's break it down. Sodium has 1 electron in its outermost shell, the M shell in this case, while chlorine has 7 electrons in its outer shell.
So they're both kind of desperate to get a full outer shell.
Exactly. Sodium can achieve a full outer shell by losing its lone electron, and chlorine can get there by gaining one. So what happens is sodium donates its electron to chlorine, and in the process, they both become ions. Sodium, by losing an electron, becomes a positively charged ion, and chlorine, by gaining one, becomes a negatively charged ion.
Opposites attract, so now those positive and negative ions are stuck to each other.
Exactly. That electrostatic attraction between the oppositely charged ions is what forms the ionic bond, holding them together in a crystal structure. It's pretty amazing when you think about it. The simple act of transferring an electron creates this whole strong bond that makes table salt possible. Figure 1.11 in the book shows how those sodium and chloride ions are arranged in a neat cubic crystal lattice.
All right, that makes sense. So in ionic bonding, it's a give and take relationship, right? What about when atoms decide to share electrons instead of giving them away?
That's called covalent bonding, and it's another super common way for atoms to get their full outer shells. A classic example here is the hydrogen molecule, H2. Each hydrogen atom only has one electron.
And they both need one more to get that stable, full outer shell.
Right, so instead of one hydrogen giving its electron to the other, they decide, hey, let's share. By sharing their two electrons, both hydrogen atoms effectively have a full K shell, just like helium.
So they're both happy and stable because they're sharing.
Exactly, that sharing of electrons is what creates the covalent bond, and it's super strong. Now, we should also mention metallic bonding, even though it's not covered in detail right at the start of the book.
Yeah, metallic bonding's got to be important considering how many engineering applications use metals.
Definitely. In metals, the bonding's a little more communal. The outermost electrons in the metal atoms, they're not really associated with any single atom anymore. They're kind of free to roam around the whole metal structure.
So it's like a sea of electrons surrounding a bunch of positively charged metal ions.
Exactly. That's the common analogy. And that electron sea is responsible for many of the properties we associate with metals. You know, their good electrical conductivity, their shiny appearance, their malleability.
Before we move on from atomic bonding, there's one more type of interaction that's mentioned: van der Waals forces. The book says they're important for understanding polymers, which we'll get to later.
Yeah, van der Waals forces are a type of weaker attraction that can exist between molecules. They're not as strong as ionic or covalent bonds, but they can be significant, especially in large molecules like polymers, where you have a lot of these forces acting together.
I remember from chemistry that they have to do with temporary fluctuations in electron distribution that create momentary dipoles in molecules.
That's exactly it. These fluctuations in electron density create these temporary positive and negative regions in molecules, and these opposite charges can then attract each other.
So even though they're weak individually, when you have a lot of these van der Waals interactions, they can collectively influence how the polymer chains interact with each other.
Precisely. They play a big role in determining things like the polymer's flexibility, its melting point, and its strength.
All right, we've now laid a really solid foundation with atomic structure and bonding. Now let's zoom out a bit and think about how those atoms actually arrange themselves in the materials we use every day, especially in metals. The book talks about crystal structures and imperfections, which sounds kind of counterintuitive. Wouldn't we want a perfectly ordered structure?
You might think so, but it turns out that imperfections in the arrangement of atoms are not always a bad thing. In fact, they can have a huge impact on a material's properties, like making it stronger or more ductile.
I guess nothing's ever truly perfect, even at the atomic level.
Exactly. So let's start with how metals solidify. When you cool down a liquid metal and it starts to turn solid, it doesn't just become a solid block all at once. It happens gradually, with tiny little crystals called nuclei starting to form at various points throughout the liquid.
These nuclei are like the seeds for the solid metal to grow from.
Exactly. And those nuclei, they tend to form around impurities or imperfections that might be present in the liquid metal. It's like they need a little something to latch onto to get started.
So it's not a perfectly uniform process happening all at once.
Right. These nuclei then grow outwards, kind of like branches on a tree. They form these tree-like structures called dendrites, actually. Figure 2.3 in the book shows a really cool micrograph of these dendrites forming in an aluminum alloy.
So as these dendrites grow and grow, eventually their branches bump into each other, and that's how you get the final solid metal.
Precisely. Those dendrites keep expanding until they fill up the entire space, and that's how you get the grains that make up the solid metal. Each grain originates from a single nucleus and has its own unique crystallographic orientation.
Okay, so each of those grains is like a tiny individual crystal.
That's a great way to think about it. Now, ideally, within each of these crystals, all the atoms would be arranged in a perfectly repeating orderly pattern, a crystal lattice.
Like those neat, orderly structures you see in chemistry textbooks.
Exactly. But like we were saying, in the real world, nothing's ever perfect. These atomic arrangements always have some flaws or imperfections. And like I mentioned, these imperfections actually play a crucial role in determining the material's properties.
It's almost like they're there for a reason, not just random mistakes.
That's an interesting way to think about it. They do influence how the material behaves. We can group these imperfections into two main categories: point defects and linear defects, which are also called dislocations.
Okay, so let's start with the point defects. What are some common examples of point defects in the crystal lattice?
Well, imagine that perfectly ordered lattice, like a three-dimensional grid of atoms. Now, a point defect is like a tiny disruption, a little error in that grid, usually involving just one or a few atoms. One common type is a vacancy. It's literally an empty space where an atom should be, just like sometimes, there's a missing piece in a puzzle.
It's like an atom just didn't show up for work that day.
Something like that. Another point defect is a self-interstitial. That's where an extra atom of the same type as the rest of the lattice squeezes itself into a space where it doesn't really belong.
So it's like that atom's trying to crash the party, but it doesn't quite fit in.
Exactly. You can also have substitutional defects, where a foreign atom, a different element, replaces one of the host atoms in the lattice. And then there are interstitial defects, where a smaller foreign atom occupies a space between the host atoms.
Okay, I'm getting a good picture of these point defects. They're like tiny disruptions in the otherwise perfect lattice. Now, what about these linear defects, the dislocations? They sound a bit more complicated.
Dislocations are line defects, meaning they extend in a line through the crystal lattice. They involve a shift or distortion in the arrangement of atoms along a particular direction.
The book talks about edge dislocations and screw dislocations as the two fundamental types.
Yes. An edge dislocation is like having an extra half plane of atoms inserted into the lattice, as you can see in figure 2.12. It creates a kind of step in the crystal structure, with a region of compression above the dislocation line and a region of tension below it.
The book uses a really helpful analogy to visualize this like a ruck in a carpet.
Right. Imagine you're trying to move a heavy carpet across a floor. Sliding the whole thing at once is really difficult, but if you create a little fold or ruck in the carpet, you can push that ruck across much more easily.
So you're just moving the fold, not the whole carpet.
Exactly.
Yeah.
Similarly, when a stress is applied to a metal, an edge dislocation can move through the lattice in a step-by-step manner, allowing the metal to deform permanently. Figure 2.13 shows a nice illustration of how this works.
Okay, that analogy makes a lot of sense. Now, how does a screw dislocation, shown in figure 2.14, differ from an edge dislocation?
Think of a screw dislocation as a spiral ramp of atoms winding around a line defect. Unlike an edge dislocation, where the dislocation line is perpendicular to the slip plane, the plane on which the atoms move, in a screw dislocation, the dislocation line is actually parallel to the slip plane.
So the direction of the distortion is different, kind of like a twisting motion rather than a shearing motion.
That's a good way to think about it. In reality, many dislocations in materials are a bit of a hybrid, having both edge and screw components forming curved lines.
So it's not always perfectly one type or the other. They can get pretty complex.
Definitely. And here's where it gets really interesting. These dislocations don't just exist in isolation. They can interact with each other.
Meaning they can either attract or repel each other depending on their orientation?
Precisely. If you have two dislocations of the same sign, for example, two extra half planes both inserted from the top, they will actually repel each other, as you can see in figure 2.16. It's like trying to force two magnets together with the same poles facing each other.
So their stress fields, those regions of compression around them, will interact negatively, pushing them apart.
Right. On the other hand, if you have two dislocations of opposite signs, their stress fields can cancel each other out, allowing the dislocations to annihilate each other, as shown in figure 2.1 here.
So they effectively disappear, reducing the number of dislocations in the material.
Exactly. And this interaction between dislocations has huge implications for a material's strength.
Because if I'm following you correctly, the more dislocations there are in a material, the harder it becomes for them to move around and for the material to deform.
That's spot on. A higher density of dislocations actually strengthens the material. It's like trying to walk through a crowded room. The more people there are, the harder it is to get around. The same thing happens with dislocations.
So as dislocations try to move through the lattice, they run into each other, they get tangled up, and that makes it harder for the metal to deform permanently.
Precisely. This increased resistance to deformation translates directly into a higher yield strength, making the metal harder. And this is the principle behind work hardening, which occurs when you shape or deform a metal at room temperature.
But there are also times when you need to soften a metal that's been work hardened, right? The book mentions heat treatments like recovery, recrystallization, and annealing to accomplish this.
Exactly. These heat treatments are essential for manipulating the dislocation density and controlling a material's properties. Let's start with recovery. It occurs when you heat a work-hardened metal to a moderate temperature, typically between zero point 0.3 and zero point 0.4 times its melting point in Kelvin.
So not crazy high temperatures, but enough to give those atoms a little wiggle room.
Exactly. And at this temperature, you get some diffusion, meaning the atoms can start to move around a little bit. This allows the dislocations to rearrange themselves, reducing their density and relieving some of the internal stresses that built up during cold working.
So recovery basically relaxes the material a bit.
Right. It makes it slightly softer and more ductile without significantly changing the overall grain structure. But if you want a more dramatic softening, you need to go up to recrystallization.
And that happens at even higher temperatures.
Exactly. During recrystallization, completely new, strain-free grains start forming within the old, deformed grains. These new grains have a much lower dislocation density, and as they grow, they eventually replace the original deformed structure.
So you essentially get a brand new, less stressed microstructure.
Exactly. And the metal becomes much softer and more ductile, making it easier to work with again. Annealing is a heat treatment process that includes this recrystallization step.
Okay, so recovery is like a gentle massage, while recrystallization is a full-blown makeover for the material.
That's a great analogy. The book also talks about something called dislocation climb, which sounds kind of interesting.
Yeah, is that like a way for dislocations to maneuver around obstacles in the lattice?
You got it. Dislocation climb, illustrated in figure 2.19, allows an edge dislocation to move in a direction perpendicular to its normal slip plane. This usually involves the movement of those vacancies, the missing atoms, in the lattice. If vacancies move to the extra half plane of the edge dislocation, it's like the dislocation climbs up.
I see. So vacancies act like stepping stones, allowing the dislocation to move in a different direction.
That's a good way to think about it. Climb lets dislocations get around things they couldn't otherwise move past just by slipping, and it can also lead to the annihilation of opposite sign edge dislocations.
So climb plays a role in both making the material more ductile and reducing the number of dislocations.
Exactly right. Finally, how do all these dislocations form in the first place, particularly when a metal is being deformed? The book mentions something called the Frank-Reed source as a key mechanism for generating more dislocations.
The Frank-Reed source, it sounds like a science fiction weapon or something.
It does have a kind of futuristic ring to it, doesn't it? But it's actually a pretty straightforward concept. Imagine you have a segment of a dislocation line that's pinned at 2 points in the lattice. When you apply a stress to the metal, this pinned segment bows out, kind of like a string being pulled taut.
So as the stress increases, this bowed out segment eventually circles around and reconnects with itself, creating a new loop of dislocation.
Exactly. And this new loop is free to move and contribute to more deformation. Meanwhile, the original pin segment is still there and can keep bowing out and creating more loops. Figure 2.2 shows a schematic of this process.
So it's like a little dislocation factory churning out more and more dislocations.
Exactly. And this process can really ramp up the number of dislocations in a metal. A typical manufactured metal might start with around 106 to 108 dislocations per square centimeter. But after being significantly deformed, this can increase to a whopping 12 dislocations per square centimeter.
Wow, that's a huge jump. It really highlights how dynamic and complex the internal structure of a metal is.
It does. And all these tiny defects, they might seem insignificant, but they really dictate how a metal behaves in the real world.
All right, that's a great deep dive into metal structure. Now let's move on to what happens when we start mixing metals together. We get alloys.
Alloys are essentially mixtures of metals. or sometimes a metal with other elements added to modify its properties. And understanding how these mixtures behave when you heat them up and cool them down, particularly during solidification, is super important for making useful engineering materials.
And to do that, we use phase diagrams, which I have to admit can look a bit intimidating at first glance.
Oh yeah, phase diagrams can be a little daunting if you haven't seen them before, but they're really just maps that help us understand what phases are present in an alloy at different temperatures and compositions.
So a phase refers to the state of matter, solid, liquid, or gas. But for alloys, we're mostly dealing with solid and liquid phases.
Exactly. A phase diagram shows us, for a given composition of an alloy, at what temperature it will start to melt or solidify, and what phases will be present at different temperatures as it cools down from a liquid.
And the book starts by looking at the solidification of a pure metal like copper. What's the key difference between the solidification of a pure metal versus an alloy?
With a pure metal, like copper, it solidifies at a very specific constant temperature. Like there's no ambiguity, bam, solid at this temperature, liquid above it. For copper, that temperature is 1010 degrees Celsius.
So there's no range of temperatures involved.
Right, and during that transition from liquid to solid, both the liquid and the solid will coexist at that temperature until all the liquid is transformed into solid.
It's all at equilibrium, meaning the system is stable at that temperature. Figure 3.3 shows a nice cooling curve for pure copper, where you can see that temperature plateau during solidification.
Precisely. Now, with alloys, things get a little more complicated because they're mixtures, right? So instead of a single melting or solidification point, they usually solidify over a range of temperatures.
So instead of a sudden transition, there's a more gradual process as the different components solidify at slightly different temperatures.
Exactly. And to see how this plays out visually, we use those phase diagrams we were talking about. For example, figure 3.5 shows the copper-nickel system, which is a fairly simple one.
And there are some important lines on that diagram called the liquidus and the solidus.
Right. The liquidus line tells you the temperature at which an alloy of a certain composition will start to solidify when you cool it down. Above that line, it's all liquid.
So if I have a 50-50 mix of copper and nickel and look at the liquidus line, I can see it starts to solidify at around 1250 degrees Celsius.
Precisely. The solidus line, on the other hand, tells you the temperature at which the alloy is completely solid. So below that line, it's all solid. In between those two lines, you have a mixture of liquid and solid.
So for that 50-50 copper-nickel alloy, looking at the diagram, it will be completely solid by around 1200 degrees Celsius.
That's right. And understanding the liquidus and solidus temperatures is crucial for processes like casting, where you need to know when the metal is fully liquid and when it's completely solid.
Now, the book also talks about solid solutions as a type of mixture that can form in alloys. The lead-tin system is given as an example with alpha and beta phases.
A solid solution is like a solid-state mixture, where one type of atom, the solute, is dissolved within the crystal lattice of another type of atom, the solvent. But it's not like a chemical compound where they bond together. It's more like the solid atoms are just hanging out in the spaces between the solvent atoms.
So it's like if you mixed salt and sugar together, you wouldn't get a new compound, but you would have a mixture of salt and sugar crystals.
That's a good analogy. In the lead-tin system, shown in figure 3.19, you get different solid solutions depending on the percentage of tin. At lower tin concentrations, you have the alpha phase, which is tin dissolved in a lead lattice. At higher tin concentrations, you get the beta phase, which is lead dissolved in a tin lattice.
And these solid solutions, they have a single uniform microstructure, right? They're not like a mix of different crystal structures.
That's right. It's just one phase with a specific crystal structure.
Okay.
And the properties of a solid solution depend on both the types of atoms and their proportions.
Now, there's another type of phase transformation that's mentioned in the book, eutectic reactions. And again, the lead-tin system is used as an example.
A eutectic reaction is a specific type of transformation that happens at a very particular composition and temperature for an alloy system. In the lead-tin system, the eutectic composition is 61.9% tin and 38.1% lead, and the eutectic temperature is 183 degrees Celsius.
Okay, and what happens at that magic composition and temperature?
When a liquid alloy of exactly that eutectic composition cools down to 183 degrees Celsius, it transforms directly into a very fine layered mixture of two solid phases, the alpha and beta solid solutions we were talking about before.
This is like a perfect alternating pattern of those two phases.
Exactly. And this layered microstructure is called a eutectic microstructure, and it can have unique properties. For example, the lead-tin eutectic alloy is commonly used as solder because of its low melting point.
Okay, that makes sense. Now let's talk about precipitation hardening, which sounds like a really powerful way to make certain alloys much stronger.
Precipitation hardening, also called age hardening, is a heat treatment process that you can use to significantly boost the strength and hardness of specific alloys. And it's all about controlling the formation of very tiny particles, called precipitates, within the alloy's microstructure.
So we're again manipulating the material at the atomic level to achieve the desired properties.
Exactly. And one common example is the aluminum-copper alloy system. The book focuses on an alloy with 96% aluminum and 4% copper. To do precipitation hardening, you first do solution treatment.
And solution treatment involves heating the alloy up to a pretty high temperature, right?
That's right. You heat it up to a temperature where all the different alloying elements dissolve completely into a single, uniform, solid solution, kind of like dissolving sugar in water.
So it's all mixed up at the atomic level.
Exactly. But at this high temperature, that solid solution is actually supersaturated, meaning it's holding more of the dissolved element than it normally would at room temperature. And that's the key to precipitation hardening.
So it's like the solution is forced to hold more stuff than it really wants to.
Precisely. Then you quickly cool the alloy down, usually by quenching it in water. This rapid cooling traps the solute atoms in that supersaturated state because they don't have enough time to diffuse and form separate phases.
So the material is kind of in this unstable state, holding all this extra stuff that it doesn't really want.
Exactly. And now comes the aging step. You reheat the alloy to a much lower temperature and hold it there for a specific period of time. At this lower temperature, those excess solute atoms become more mobile and start to diffuse, coming together to form those tiny precipitates we were talking about.
So those precipitates act like little obstacles, making it harder for dislocations to move through the lattice.
Yeah, not. And that increased resistance to dislocation movement is what makes the material stronger and harder. The size and distribution of these precipitates are critical to getting the desired strength.
So it's all about fine-tuning those little particles within the material.
Exactly. For precipitation hardening to work, the solubility of one element in the other has to decrease as the temperature drops. So on the phase diagram, like figure 3.25, that solvus line, which marks the boundary of the single-phase region, needs to have a noticeable slope. If it's flat, you won't get precipitation hardening.
All right, that makes a lot of sense. Now let's switch gears completely and talk about polymers, which are entirely different beasts from metals.
They are. Polymers are amazing materials. They're basically long, chain-like molecules made up of repeating units, kind of like a long chain of paper clips, all linked together.
And those long chains, they can be arranged in different ways, right? That's where the distinction between amorphous and crystalline polymers comes in.
Yeah, exactly. In an amorphous polymer, those chains are all jumbled up like a bowl of spaghetti.
Right.
There's no real order to their arrangement.
Just a big tangled mess.
Pretty much. But in a crystalline polymer, sections of those chains line up in a nice, orderly, parallel fashion, forming these tightly packed regions called crystallites.
So it's like parts of the spaghetti strands have suddenly decided to be neat and organized.
That's a great way to think about it. Figure 4.1 shows a nice visual comparison of these two types of structures.
But in reality, most polymers aren't completely amorphous or completely crystalline, right?
That's right. Most polymers are actually semi-crystalline, meaning they have both amorphous and crystalline regions within them. And the degree of crystallinity, or the proportion of crystalline regions, has a big impact on the polymer's properties.
So the more crystalline a polymer is, the stronger and stiffer it tends to be.
Exactly. When those chains are neatly aligned in the crystalline regions, they're packed much closer together, allowing for stronger intermolecular forces to act between the chains.
Those van der Waals forces we were talking about earlier come into play here, right?
Yes, they play a big role in polymers, especially in the crystalline regions. Those temporary dipoles create attractive forces between the chains, holding them tightly together.
So the more crystalline regions there are, the stronger those intermolecular forces are, and the stiffer the polymer will be.
That's the general trend. You can see this clearly in Table 4.3, which shows how the tensile modulus of polyethylene increases with increasing crystallinity.
Okay, that makes sense. Now, what about the glass transition temperature, Trag, which the book highlights as a really important concept for polymers?
The glass transition temperature is the temperature at which an amorphous polymer transitions from a hard, brittle, glassy state to a softer, more rubbery state. It's all about the mobility of those polymer chains.
So below 2G, the chains are kind of locked in place and the polymer is rigid.
Precisely. They can only vibrate a little bit, but they can't really move past each other.
Mm.
But above chi, the chains gain enough thermal energy to start wiggling around and sliding past each other, making the material more flexible.
It's like the polymer has gone from frozen solid to thawed out.
I like that analogy. And figure 4.16 shows a nice illustration of how a polymer's stiffness changes dramatically around its chi.
So the mechanical properties of a polymer can completely change depending on whether it's above or below its chew.
Absolutely. Below chi, a polymer is typically brittle.